All right, so thank you everybody for taking the time to come here, and thank you to PER. So today I'm gonna talk about research directions in extreme scale shared memory architectures. You'll see this is very technical, and it is to show that there's a lot of things to do still in computer architecture. Before I start, however, I want to say a few things about PER, when I met him and how. So I was a graduate student at Stanford back in 1990. And I saw this visiting scholar, or you're a visiting scholar who was visiting the group. I was in Hennessy's group, he visited Gupta, but we were in the same group. And I was in the meetings with him, and this guy is really smart. Every comment that he makes really makes sense. And then that year, he published 2 ISCA papers, right? Or 2 or 3. So I was really amazed how productive he was. He was working very hard. And so since then, I had a lot of admiration for him, because I think he's very smart. And also for his students. Frederick came to Illinois once, and I know that he's also a very smart guy. So I'm very happy to be here. So let's get started here. So you know that there's a huge acceleration in progress in transistor integration. And there's lots of stuff that companies are doing, like this Xeon Phi, 3D stacked memory, and so on. So what can we do as researchers? Is there anything that we can do? So after some of the talks that we heard today, that everything is done, I'll take the opposite approach. Everything has to be done. So what research can be done in computer architecture? If you work on very high energy efficiency, that's a safe thing to do. Okay, so there's lots of things to do in energy efficiency. There's also lots of things to do in parallelism, which is what PER is working on, and ease of programming. And now, as we have seen, in security as well. So what I'm going to try to do is just go over some of the topics that I think are promising, and maybe you'll see that some of these topics agree with what I'm working on. So let's start with energy efficiency. So the first thing is we have a temptation to think about, let's work on new devices, because now CMOS is kind of dying. Let's look at architectures with other devices. Not as far as quantum computing, but perhaps other things. So there is this graph from Intel where they're looking at all different types of devices. Here you have the speed. This is the speed, and this thing is the energy consumption. CMOS is here, and then there's a bunch of other stuff. This is tunneling FET. So what we did is we looked at building a processor and a GPU where you mix CMOS for the parts of the processor that are latency intolerant, meaning that they need short latencies, and the parts of the CPU that are throughput intensive, we put these other transistors, which are TFETs. TFETs are much slower, an order or 2 of magnitude, 1 order of magnitude, but much more energy efficient, 2 order of magnitude. So we have a paper in ISCA that talks about this. So what is the idea is to have, or the vision is this heterogeneous architecture, where you have in the same die, you have transistors of different types, right? We were very exciting, and I've been working with Intel, or trying to work with Intel, and sending emails and papers and ideas to a group in Intel and never getting anything back. So this is kind of a warning, which is this is very important for Intel now to figure out what is the next type of devices, and it's the core of their company. They don't appreciate researchers really messing up with this. So this, I'm not sure, is a good idea, to work on trying to, as architects, work on devices that are really the bread and butter of Intel. What else can you do in energy? Well, there is 3D stacking. That's another important area. So we're going to see, as time goes by, people stacking more and more on a stack, right? So we're putting, say, a processor and a bunch of memory dies on top. The key of the game here is thermals. Okay, so if you want to make an impact here, think about thermals. If you reduce the temperature, you can increase the frequency and therefore improve the performance for the same temperature. Make sense? Suppose I have a technique that is able to reduce the temperature. Then I can crank up the frequency and reach the same temperature as before and improve the performance. So what have we done in this area? One, so let me go here. We've been able to put thermal TSVs. You know what TSVs are? These are vias. So we put thermal TSVs, and we align them with what's called a dummy microbump. A dummy microbump is what connects two dies. So by aligning the dummy microbump and the thermal vias, we have these columns of conduction, right? So you can move the heat faster from the bottom where you have the processor to the heat sink. And that reduces the temperature because you have more conduction. And as a result, you can increase the frequency. And also another side effect is that you can put the hot parts of the processor around these thermal vias so that the heat quickly moves up. Okay, so that's one idea. This is a micro paper. Another problem with 3D stacking is that the package is proportional, the cost of the package, to the number of pins that you have. Can we think of techniques to reduce the number of pins? Okay, so think about this. Now, we have, if you have a processor die, the power delivery network of the processor die is independent of the power delivery network of the memory dies. And each of them is connected to their own power and ground pins. So whenever somebody designs a chip like this, it has to put as many power and ground pins for the worst case of the processor power and for the worst case of the memory power. In reality, if you run a program, it is either memory bound or processor bound. So you don't need the worst case. So what we did is we connected the two power delivery networks, and we steal power. Whenever the processor needs power, the memory is not very active, we steal the power. As a result, we need fewer chips, fewer pins, 30% fewer pins, and that reduces the cost. So that's another example. Moving on. What we're seeing now is that every single drop of energy waste matters. We want to have systems that are extremely energy efficient. So what we're looking at is at controllers, and the state of the art is people use controllers that use heuristics. You know, if the temperature is too high, then reduce the frequency. If the processes are not well utilized, then do this thing. All heuristics. Obviously, this doesn't work. If you use heuristics and the system gets complicated, it's not going to work. It's going to be very efficient. Look at this. This is an AMD Ryzen system. It has a GPU chip and then what's called the CPU cluster, which has two CPU chips, each of them 4 cores. Each of these systems is built by different companies. Now, how can you build something and then you take something from somebody else? How do you control the whole system? So here is a research area. Build controllers that are composable, basically. Okay? Controllers that use control theory, because that's how you get the maximum robustness, but they are composable. Okay? So what we do is we've been working on this area for a while. The idea is to use control theory to build controllers that control cores, CPU chips, GPUs, and then up in a hierarchical manner. Okay, so in this case, what we have, for example, is the system is a GPU chip. You look at the power and the performance in bips, and you control the frequency, the ROP size, this was a processor, and the cache size. Okay, so here's an area where I think there's a lot to be done. Formal techniques to improve the energy efficiency. Let's move to parallelism and ease of programming. So this, even though it's an area that people have worked a lot, there's still a lot of things to do. So now we're going to have chips that have 1,000 cores. Okay, and so many idioms are such that you have a lot of threads contending for a single thing. For example, you have compare and swap that tries to increment this variable. You see algorithms like this in the operating systems. Okay, can we think of hardware or even software techniques to have efficient synchronization in these large cores? Okay, so for example, many programs use priority queues. So you have a many-core system and have a single priority queue in software. Then all the cores have to contend to put something in the tail and get it from the head of the queue. So that's very hard to do. Maybe we want to have a distributed queue, okay, where we have multiple queues and processors tend to put stuff in the local queue, and then they need to find a global best around, right? So the problem is that if you write the algorithm this way, you waste work because you make the queue things that are not optimal. So how do we balance the two things? On the one hand, we want to have kind of a priority queue, global priority queue, but on the other hand, we cannot have it with current systems because we would have too much contention. Can we think about a combination of software and hardware to be able to have good performance and basically scalability? Another problem we're looking at is graph applications. Okay, so there's lots of graph applications, but the problem is that if you read the papers, you see that there's no consensus. Okay, so first, there are some people who look at distributed systems, like let's have a huge cluster and run a bunch of graph problems there. The algorithms that you need there are not the same as the ones that you need if you have a shared memory machine. You know, one could argue that you can get better performance with a good shared memory machine than a distributed machine. Okay? Now, even within a shared memory machine, there is different types of algorithms. If you read the literature, there's no consensus on what the bottleneck are. The reason is that some algorithms are topology-driven, where you only activate the vertices of the graph that are actually active, as opposed to the data-driven, where you, in every iteration, you process all the nodes in the graph. Obviously, this is not very efficient. Even within topology-driven, there is pull versus push. So different algorithms behave totally different in terms of cache, so you're the buffer. Okay? And then there is the issue of, so I forgot what I was going to say. Oh, the data structures that you use. What data structures that you use, you have to have good locality, and as we move forward, graphs will be updatable. So not static graphs, but graphs that change with time. How are you going to do this? What kind of software algorithms do you need? What kind of hardware support do you need for that? Machine learning. Okay, so nowadays people are very happy with GPUs. But why? Because current algorithms were designed for GPUs. Now, what about if we look at ways in which the algorithms are designed for CPUs? It turns out that there is a lot of room for irregular machine learning applications. Okay? For example, sparsity. People don't like sparsity in machine learning algorithms because GPUs don't work well. But maybe CPUs work well there. Also, there is the sparsity not in the weights only, but sparsity in the activation. Given a huge neural network, DNN, now we're activating the whole thing. In reality, the brain doesn't work like this. You only activate a path in this thing, okay? Or maybe you activate multiple paths and you take a vote of which, if there's consensus. All these algorithms are not being developed because people use GPUs. Another area is on-chip wireless. This is something I'm working on, is what if we put a little antenna in each of the cores, in 1,000 cores, so that they communicate? What can you do with this? You can do broadcasts very cheaply. Okay? So you can have, say, this here broadcast a value with very short latency, not a lot of bandwidth. So idioms that were very hard to support in conventional hardware, you can support this easily. But that's another area. Programmability. Programmability, we've been looking at conventional systems, but now people are programming in scripting languages, like, for example, JavaScript, Python. All these languages, at compile time, you know very little information, which means that at runtime, you have all these data structures. You have hash tables, linked lists, lots of things that you need to do. Very low overhead. Why not have some architectural support for these languages? Okay, I'll give you an example of what one can do. Whenever you issue an access to an object, this is a read or a write, you don't know what is the type at runtime, at compile time. So what happens is that you build what's called the inline cache, which is code in a dispatcher that checks, is this object of this type? If so, you jump to a handler. Is this object of this type? No. Is this object of this type? No. And you find the right handler, and here you do the actual load or the store. Okay? So what if, and you can imagine that this is a lot of code and lots of branches that you cannot predict. So what we did is we have a trampoline, meaning that in here, instead of jumping to the dispatcher, we predict what is the type that you will see, and you jump to the actual handler directly, bypassing the dispatcher. Okay? How do you do this? You augment the BTB with a prediction of not the handler, not the dispatcher, but instead of the handler. But for this to work, of course, you did the prediction, you start jumping, but then you have to ensure that it is correct. So we have another table that says this entry is of this type. Okay? So I guess I don't have time to explain the details, but the idea is that you augment the hardware to record what is the type that is found at this offset, and then when you start predicting, you start jumping, bypassing this thing, and you at the end confirm that you're doing the right thing. Okay? And this is actually even a more aggressive branch predictor and BTB predictor that bypasses even the handler. It does the operation there. Another programmability issue is we are seeing that people are going crazy with virtual machines. Okay, so what happens is that we have this infrastructure in the cloud, and we have host operating system hypervisor, and then a bunch of virtual machines, and Python, and then applications. The result is that there's a huge replication of the pages. All these applications use the same pages. Can we do deduplication, which means kind of have one page and have multiple pointing to the same page? Okay, so what we did is we call this page forge. So instead of having, currently people do it in software. VMware has this thing that runs from time to time that checks pages, and if they're equal, it merges the pages. So we have an engine in the memory controller that basically continuously reads the pages and compares them, and if they are the same, then it merges them, avoiding CPU cycles and pollution of the cache. So, and another thing that this does is not just the comparison, but the hashes. You have to generate the hash quickly. To be able to say if two pages are the same, oftentimes you just compare hashes of the pages, and if they are different, you just don't compare them. So this engine does it. And now we're looking at beyond virtual machines, something that is called containers. So if you know what containers are, these are very, very, very tiny virtual machines, right? So people are now programming with lots of containers, which means that lots of replication. Okay, so people are even talking about function as a service. You call a function in the cloud, run this function for me. Huge overhead and huge replication. All this requires architectural solutions. And okay, and finally security. I don't need to tell you about security, right? There's lots of 3 minutes. Okay, lots of problems in security. So people started with caches, which is the simplest thing. So what happens here? I have a victim that runs in this cache, a spy that runs in this one, and they share an L2 cache. So what happens if you share the L2 cache? So I want to know if this one here is going to access this green thing. So what the attacker does is it fills the L2 completely. It accesses all these lines. It brings it into its cache, but it fills it, displacing the green from here, right? This is called an inclusion victim. You displace it. Then it lets the victim execute, and if the victim executes, it's going to bring the green here and here. And then all the spy has to do is re-access the lines and see if it misses here. It used to be red, now it's green. If it's green, it knows it has access to this thing. Okay, so this is a typical thing that people do. So what we have done is we've looked at ways of avoiding this problem by preventing the displacement of lines that are in some other caches. So if you need an entry in here, but that entry is in somebody else's cache, we don't displace. You displace your own. But what happens then? Intel comes along and says, let's build non-inclusive caches. This only works for inclusive caches. But let's build non-inclusive caches, right? And so they think, oh, we're safe now. You cannot displace somebody else's data because the cache is non-inclusive. But what we recently found is that you can attack the directory, not the caches. Even if the caches are non-inclusive, the directories have to be inclusive. Anything that is in the caches has to be in the directory. So hit the directory until you displace everything from the directory entry, which necessarily will displace it from the caches, right? So this thing is really starting to blossom. And then there's, of course, the issue of speculation. So what is the goal of speculation? I mean, what is, how do we make a system secure to the speculation? Make speculation invisible. That's the goal. Okay, so people will come up with solutions where you do whatever you want, but nobody can see it. Okay? All right, so I don't think I have more time now. So thank you, Per, and thank you, everybody, for your attention.